In this section, we'll look at GPS accuracy and error. We'll talk first of all about the user equivalent range errors and the problem of dilution of precision. First of all, keep in mind that the satellite clock is a very critical part of a GPS satellite system, but small drift may occur in atomic clocks on satellites. Clock corrections are calculated and transmitted with GPS signals. The upper atmosphere is another source of error. Delay and deflection in the ionosphere is quite common. The ionosphere density varies, and monitoring stations can model ionospheric conditions, calculating corrections and transmitting to satellites. This is then transmitted to receivers. The receiver clock is less stable than the atomic clocks on satellites. Satellite transmissions from two satellites are compared to correct error. Satellite orbit may vary because of conditions in space, and exceptions to ideal projected orbital conditions are modeled and may be adjusted by some US GPS receivers. The lower atmosphere, the three lower layers of the atmosphere, the troposphere, tropopause, and stratosphere, have denser conditions that may cause signal delays. Weather conditions become important as well. Greater delays may occur from satellites that are close to the horizon relative to a position on the Earth. Multipath errors are common in urban and forested environments, and reflection from objects near the ground is common. You may use mask angle to only track satellites more directly overhead the receiver. This shows the concept of various error sources in the atmosphere and on the ground as well. And so, for example, you can see orbital bias, satellite clock bias, receiver clock bias, ionospheric effects, and lower atmospheric effects as well. Multipath errors such as buildings, trees, and other features become an issue. All of these things affect the way that the signal may reach the user. Accuracy is affected by the arrangements of satellites in the constellation as well. The ideal arrangement is for one satellite to be directly overhead with three others spaced equally near the horizon. Dilution of precision, or DOP, occurs when satellites are clustered together. Horizontal and vertical DOP is measured, and positional dilution of precision, so-called PDOP, is also indicated on handheld GPS units. A PDOP of 1 is ideal, a PDOP of 2 is good. A PDOP far above 2 can cause serious problems with location. Differential correction is one way of dealing with these various error sources. Known distances between two or more receivers are used to enhance GPS readings, and a base station is used to calculate error. Correction data is recorded for use with collected data. That data is downloaded typically later after a data collection mission. Differential correction with a base station and a mobile receiver is shown here. So the base station has a role in basically adjusting the point fixes that are received by the receiver. Error correction is then calculated by the base station and is applied to the position calculated by the mobile receiver. Differential GPS includes a base station, differential correction, a rover, real-time correction, and post-processing. Differential GPS greatly enhances the accuracy of GPS data collection. This is the concept of differential GPS, with the role of a base station playing a critical part in signal correction. Post-process differential correction is another option. Static positioning is required for high accuracies of 1 part in 1 million or higher. 2 or more receivers measure positions from fixed locations over time, and dual frequency receivers are capable of this. They measure the difference in time of arrival of GPS and military signals. The U.S. National Geodetic Survey maintains an online positioning user service called OPUS. Surveyors use this to differentially correct static GPS measurements acquired with a single dual-frequency carrier phase differential receiver after they return from the field. This data is downloaded later. Measurements in a standard receiver independent exchange format are sent to NGS computers, which perform differential corrections by referring to 3 base stations selected from a network of continuously operating reference stations. GPS information is expressed in time with GPS time, GPS week data, Universal Time and UTC, which is the same as Greenwich Mean Time. Universal Time Coordinated as well. International Atomic Time also may be recorded. Datums, typically in GPS work, datums will be the WGS 84. Coordinate systems, geographic coordinate systems, geodetic latitude and longitude is then converted into a local coordinate system as needed. Elevation includes height above the ellipsoid. Elevation relative to the surface of the ellipsoid, and this is converted into orthometric height, height above mean sea level for display. Units of measurement include grid coordinates, degrees, minutes, and seconds, or digital degrees. Imperial state plane or metric UTM grid coordinates are also included. Compass declination may be used, relation to databases, and positional accuracy, comparison with known positions, is possible. This shows the concept of the circular error probable that may be used to assess and express GPS accuracy. It is based on the radius of a circle inside which there is a stated probability of fixes being located. And as you get more experience with GPS data collection, you'll learn more firsthand how the systems work and how data are collected and how to be aware of error sources and accuracy. And that concludes this section of the lecture files.